This is my final year project video of my implementation of Fabrik. Fabrik is, from preliminary research, the most efficient algorithm and produces the best results so far from what I can see with regards to sort of realism of a moving arm compared to CCD, which has the least energy approach. We're using poles to create a plane so that we can orientate all of our joints towards that pole to sort of create like an elbow effect. We go into the algorithm here with our chain length, which has to be set, and it's just simply 1 minus the joints. We have our delta, which is the tolerance we have between the end effector and the target. And we have our pole transform, target transforms. So we'll just quickly go into the algorithm itself. So here we have the reaching behavior. Once we go in, we'll see the joints rotate here towards the pole. And as we can see instantly, the difference between the behavior of Fabrik and CCD, and that CCD at this point here would have rotated just this joint. And we can see Fabrik has rotated all the joints to create a more realistic look to the algorithm. And this is the one I'll be putting most of my research and implementation ideas into, which you'll see at a later date. And we can quickly go into the code behind this now. So I'll pause this here. We can see here we're just simply getting the positions of joints, finding bone lengths, limb lengths, and see it all here. We start from the end effector, but we populate the vector from back to the front, so that the root would be at 0 and the end effector would be at 5 for this. Here it's here finding the distances to create the bone lengths and limb lengths. And so we'll get to the actual code. This is not used anymore. Okay, here. So here we have a simple check to see if the limb or the armature can reach the target. And this is just a simple check of the distance between the root, the target transformation, and the limb length of the armature. And obviously, if the distance is greater than the limb length, we can't reach it, and we just create a direction from the root to target, and we move all of our joints in that direction, and obviously preserve the bone length. And so we get into the algorithm itself, and here we have backwards. So starting at the end effector, move down, so we place our end effector at the target position, and then for every subsequent joint algorithm, we take the direction of the current joint, the next one, and we move it along the line that is created, still preserving the bone lengths. And then we do the very similar thing, the forward. Take our position, take the one before it, and then add on the direction times the bone length, and then this moves our all of our joints towards the next joint. Oh, sorry, the joint closest to the end effector. Sorry, that in that direction. And this simply makes sure that our end effector reaches the target, and then every other joint is moved towards that joint, and then we move forwards again afterwards, making sure not to move the root. And then we do a simple check. We just say if the distance between our end effector and our target is less than our delta, then we can break and stop using too many iterations because we're already there. And then we have a pole. And the way a pole works is create a plane from the previous joint. I'll open, put this to the side, this here. And so if we look at this side here, so we would create a plane, for example, for this joint, we'd create here. And we essentially project our joints to this plane. And the idea of this here is to make the distance of the projected point on the plane, the distance between that projected point of the joint and projected pole, the distance as minimal as possible. And so what we can do is we can rotate around this joint here, and it'll be a circle projected, and the minimum distance will be the closest point on that to this joint here, and this pulls all of the joints in the chain towards the pole, and that's how that works here. And this is the code here. Go back here. We can see because of the way Fabrik works, it doesn't orient. It doesn't change the position of the joint based on orientation. Using parent transforms, it just moves these joints. And so after we've finished our iterations, our loop, we have to make sure that we orient our joints properly. So we orientate our end effector to the inverse of the target, and then every other rotates from its initial direction towards the next joint in the sequence. And then we just update all of our positions. And this is where it differs from CCD, which orients the joints. This is just some code to make our chains and bones show in yeah, and thanks for watching this video. I'll see you in the next one.